In the remaining videos for today, I'm going to work a couple of example problems, one using an azeotrope, one using a ternary system. Be aware that these problems are kind of veering away from phase equilibrium and into separations. So both of these problems would fit perfectly in separations, but not quite so well in phase equilibria. I introduced them here just to give you some type of context for why you would want to do this. I think that, again, sometimes the why is missing a lot in thermodynamics, and it can be very useful to have some type of motivational example to guide you in terms of why we're even doing what we're doing. So in this problem, we have a liquid mixture of 30% acetone and 70% methanol, which is being heated from room temperature to 68 degrees C. What fraction of the mixture will evaporate, and what is the composition of the vapor phase? So it's kind of strange to say what fraction of the mixture will evaporate, assuming that it evaporates at all. So the first thing we need to do is to get some experimental data. And again, this is what the point of the whole class is. So in the remainder of phase, what we'll be focusing on is, given acetone and methanol, the system and what the composition is, how would we even obtain the data that we need if we didn't have access to it? In SEPs, what I'll do is just give you the data. So I'm going to start with that for this problem. So here we go, voila, we have some equilibrium data. Notice we have a minimum boiling azeotrope in this system, but this is going to allow us to solve the problem. So let's first draw a picture. This looks like a closed system. I'm just going to draw a cylinder with some liquid in it, liquid mixture that is 30% acetone, 70% methanol. And I'll make it, shade it so that it looks like a liquid. All right, awesome. So it's starting at room temperature, and we're going to heat this up to 68 degrees C. So T1, 25 C, T2, 68 degrees C. And we want to find what is the fraction of the liquid that has evaporated and what is the composition of that vapor. So two completely different questions that we're asking here. So all I have to do is go to my TXY diagram. At 30% acetone, my room temperature is going to be somewhere far down there, so far below 60 degrees. Doesn't really matter, it's going to be all liquid. We're going to heat this now, continue up until we hit 68 degrees. So because our intersection of the coordinates is in the two-phase region, that tells me that I do have some portion of the mixture that is evaporating. Not all of the mixture is evaporating. Say I heated it up to 72 degrees C or so, then it would evaporate 100% of the mixture. Whenever I'm in the two-phase region, I need to draw myself a tie line, and I can trace down what the compositions are. So I'll draw straight lines down to measure what the compositions are. So this will answer the second question immediately. What is the composition of the vapor phase? So by looking at my diagram, I can read this point. My vapor phase, remember this is the dew point curve, is 30, we'll call it 35. Sometimes precision when you're reading these diagrams is a little bit off. 35% acetone, which means that the other 65% must be methanol. And in the liquid phase remaining behind, let's say I've got 19% acetone and 81% methanol. So that is the composition of the vapor phase. We've already solved that one. 35% acetone and 65% methanol is the answer there. Now, how do you figure out what fraction of the mixture will evaporate? That's a slightly different problem. So my liquid phase is 100% at the first time point, and it's going to be, there's going to be a fraction in the liquid phase and a fraction in the vapor phase afterwards. So I can do that two different ways. One way is just the material balance way. So material balance method. And I could say that because this is a closed system, my number of moles initial has to be equal to my number of moles final. So my material balance method, I have a better notation for this in SEPs, but I'll call this moles in the liquid initial, moles in the liquid final, moles in the vapor final. So I'll say that moles in the liquid in the initial must be equal to moles liquid final plus moles vapor final. And then because I know what the composition is, I can do, how many unknowns do I have here? I have 3 unknowns in this equation, but notice I haven't set a basis. So I'm going to set a basis of 100 moles for moles in the initial case. Notice we are asked for the fraction of the mixture that is evaporated, not the amount. So that clues me in that I can set a basis here. Remember, in general, you can set a basis anytime that you have not set the size of your system. Keep in mind, it doesn't make any sense to ask what amount of the mixture will evaporate, because if the problem doesn't specify, then you can't reasonably be asked to calculate what the amount is. So say this is equal to 100, and then we have a material balance that we can use to get the rest. So I can say that 0.35% of the vapors. Sorry about that. Mail time is always fun. I lost my train of thought here. I need to do a material balance on acetone. Right, so 35% is my mole fraction of acetone in the vapor phase. So that's NV final plus 0.19 NL final. And I know that that must be equal to whatever I had initially. So my initial composition of acetone was 0.30 times 100. So here I have a system of 2 equations with 2 unknowns that I can solve for the moles final and the moles in the liquid final and the moles in the vapor final. So the solution procedure here is to substitute would probably be the easiest. So solving, I'm going to solve for NL final and just plug that in. So 0.35 NF final plus 0.19 times 100 minus NV final is equal to 30. And then solve that. So 19.19 times 100 is 19 minus 0.19 NVF equals 30. Okay, solve this point. So take the 19 over to the other side, gives me 11 divided by 0.35 minus 0.19, which is 0.16, correct. So this tells me that NV final is 68.9 moles, which then back solving for NL final, 31.1 moles. I do that. I'm just going to double check my math. Yeah, my math is right. The only reason why I was hesitating is that it doesn't look correct with my other method that I'm going to show you. So reading these diagrams is sometimes a little bit hard because it's very hard without zooming in to get the exact points here. There's some leeway that's allowed when you're just reading these by hand. But if you had access to Excel or something, you could calculate this much more accurately. Or when we have models for these bubble point and these dew point curves, which is the point of this class. When we have actual models that we can use, we can be a little bit more precise. But if I just give you what the diagram is, sometimes it can be a little bit trickier. So we'd say 68.9% is in the vapor phase. Another way that you could solve this problem is called the inverse lever rule. And in the inverse lever rule, you simply take the distance of the tie line and you relate it to the percentage of the way that you are. So the inverse lever rule here. For this one, I am going to have to zoom in. So you say that the fraction, that's going to be the fugacity. Let's see, what variable should I use for the fraction? I'm just going to say moles vapor over moles liquid. You know what? I'm going to say moles vapor over moles total is equal to, and then I'm going to use these Greek letters alpha and alpha plus beta. That's oftentimes how you see this rule laid out. So this is simply a geometric problem solving procedure. So if I zoom in really far here, and I take the line distance. This is what we call alpha. So it's just the distance from the actual point to the bubble point, and then this line segment is going to be beta. So alpha plus beta is the total length of the tie line. So these are lengths. So if you just take a ruler and you measure what percentage of the way that we are. I wonder if OneNote has a ruler function. I think it does, but I'm not exactly sure how to use it. Let's just say the whole distance of this line segment, alpha plus beta, is 1 centimeter. Then you would measure what alpha is, and say in this example, we'd say that alpha, I don't know, if alpha plus beta is 1 centimeter, we'd say alpha is 0.8 centimeters. Then going back to my equation for the inverse lever rule, and it's called the inverse lever rule because here we're measuring the moles of vapor. It's the opposite of what you would expect. So that's why it's the inverse. Alpha over alpha plus beta. Another way to think of it is that if my point is closer to the dew point curve than the bubble point curve, it makes sense that I should have more vapor than liquid. So just take the ratio of the length. So 0.8 divided by 1. We'd say that the vapor is 80% in the vapor phase. Now, why did I get slightly different answers doing it the material balance way versus the inverse lever rule way? And again, it goes back to how I read the diagram and saw that I had 35% acetone and 19% acetone. Notice in the inverse lever rule, this was only good for telling you what the fraction in the phases are, not what the compositions are. So use for determining compositions, not, or determining fractions in phases, not compositions. So again, this is a little bit of a flash forward. Typically, students that are taking phase would take separations at the same time, so this might make a little bit more sense in that context. But these two courses are very closely intertwined. Phase equilibria is the theory behind why separations occur, and then separations is a practical application of that knowledge. So I think there's room in both classes to kind of overlap a little bit, and that's one example of this. So this is how you would use azeotropes. Notice that if I were to go closer to the azeotropic composition, so let's say, for example, I had 60% acetone instead of 30, and I heated it up to 62 degrees. Notice how the data points are a lot closer together here, or the vapor, or the curves are a lot closer together here. Oops. And that is going to indicate that I'm going to have more difficulty separating these two things because they're going to be a lot closer together. But that's enough for this problem. In the last video for today, I'll do a ternary system.